Hello guys, in this video I'm going to be talking about subspaces. Okay, so till now we have seen the vector space. So what is a vector space? It has four things. It has a vector, it has a field, it is any two vectors can be added and they should again belong into the same vector space, and they can be multiplied by a scalar, and that scalar comes from the field. So this is something that we have seen. Now let's go ahead. So this was how I introduced the vector space to you all. So we can assume a vector space to be a room where these different vectors live inside the room and they are closed. So this is the door and the door is closed under addition and scalar multiplication. So no matter which vector you take, any vector you take from this space, when you add both of these, they should again be some vector in this space. And if you multiply with a scalar alpha a or b that comes from a field and do this, so this is also known as a linear combination. So if you have a linear combination of two vectors v1 and v2, if v1 and v2 belong to vector space v, the linear combination of that is v3 should also belong to the same vector space. So that was our definition of vector space, right? Now further we can inquire whether if we take a small section or a small subspace of this vector space, okay, so small subspace of this vector space, so this is a subset. So now I'm only considering these vectors that are inside this box. So if I just consider this, will it be a vector space? This is a question. So if I just take a subset of the vectors inside the vector space, will it be a vector space? Okay, this is what we are going to figure out in this video. Let's see. So let us consider our vector space as R2. So this is the two-dimensional vector space. So the vector can be represented as two values, x and y, so the x and y coordinates, and we'll take a and b, which is again scalar, that is belonging to a field, and the field is real numbers. Okay, so a and b will be some scalars which actually belong to the real numbers. Okay, now let us define some s on this vector space v. So this is our vector space, the 2D plane. Now let me define a s which is actually a subset of v, and it is defined like this. So s is equal to all x comma y, so all x comma y's where such that, so this means such that, this line, x square plus y square is equal to 1. So this is our equation of circle. So what s means is that it means all the points that lie on this circle that are in the center. I mean the center of the circle is at origin and the radius is 1. Okay, so that comes from this equation. So s is all the points that lie on this circle, this circumference, all these points. So the question is S a vector space? If I just consider points on this circle, can I say that only these points that are on the circle are a vector space? Okay, so we can right away reject this by looking at 0. So we know that 0 is not present over here. I mean, none of these points have 0. Since there is no 0 vector in this particular set, so hence we can say S is not a vector space, because it is very important for a vector space to have 0. And since this space that we have defined, this S that we have defined, does not contain 0, hence we can directly say that it is not a vector space. So this subset of the vector space, this circumference of points, is not a subspace. Okay, let's see another example. So now let us also include this 0. So let me say, okay, let us take x square plus y square less than equal to 1. So it contains all these points that are inside the circle. Okay, so now 0 comes inside it. Now can we say that this set that we have, this circle, all the points inside this circle, can they be a vector space is the question. Okay, so again, let's say if I take 2 points, one point is this 1 comma 0 and another point is this 0 comma 1. Both of these points lie in this space, this blue color shaded region. But if I add both these 2 points, if it would have been a vector space, then if I add these 2 points, the addition should also be inside the vector space, right? But when I add these two, I get a point 1 comma 1 which is outside the vector space, right? So this point is not inside this shaded region. Hence, we can say that okay, this is also not a vector space or not a subspace. Okay, so the first, and so this was also not a vector space or not a subspace, and this is also not a subspace. Okay, so let's see if there is a scenario where we can have a subspace. Okay, right, so let us take this. Now S is equal to all x comma y's where y is equal to x. So here I have a straight line with slope 45 degree. So basically all x coordinate value is equal to the y coordinate value. So that is our y is equal to x line. Okay, everything is same. The vector is r square, the vector space is r square, the field is r. And now let us see if we take 2 points. So let me take a point a comma a. Okay, so why is this a comma a? Because we have the definition such. So y is equal to x. That means the x coordinate, if the x coordinate is a, the y coordinate should also be a, right? So we take a comma a and then we'll take b comma b. So now if we add both these, so a comma a and b comma b, what we get is a plus b. What we get is a plus b, a plus b. So that, now again the x coordinate and the y coordinate of both these is same, a plus b, a plus b. So that will be again some point on this line, right? So since we have defined this line as our space, so S is now a subset of these points, all the points that lie on this line, right? So no matter what you do, no matter you add both of these, you multiply this with a scalar that is a and b or so on, whatever you do, what will happen is you will always land up at this line. You will never come outside this line. You will always land up on this line. Also, you can say that the zero vector is also present over here. So here, this we can say is a vector space, or this is a subspace. This line over here is a subspace. Okay, so let us formally just define subspaces. So not all subsets of vector space can be a subspace. Given a vector space Vf, so the vector space V with a field F and dot and plus, we can say S is a subspace over the field F, over the same field F dot plus, if and only if there lies any vector x comma y. So if you take any two vectors x comma y, that is this a and b, if I consider this as my subspace, take any two vectors. If you have the linear combination of these two vectors, they should also lie in the same space. That is it. So no matter what you do, you add, you multiply it with a scalar that comes from a field, the addition or the linear combination should lie in the same subset or the same space. If this goes outside the space, then I won't say S as the subspace, right? So here we can define a trivial subspaces. So given this R square as my vector space, the R square is can be known as a subspace. I mean, take all the vectors that are there in this. So R square is also a subspace of R square because it has all the vectors, that's all. And 0, the only vector 0, if I just consider 0, this is also a subspace. So these are known as the trivial subspaces. So the 0 vector over here, So if I just consider this dot, this is also a subspace because this follows all the rules. So you multiply so you take a vector. Now this has only one vector, so you will be able to take only one vector. You multiply it with any scalar that comes from a field. No matter what you multiply it, you always will land up with 0. So these two are known as the trivial subspaces. So that was all for this video. In the next video, we'll see examples of the different subspaces. Thank you so much for watching. Thank you.